Hello, everybody, and welcome. Can you hear me? Is that on? Welcome to our fifth and final edition of our hackathon from our workshop. So, we're very happy and excited to have you here. My name is Jose. I'm a PhD student in the Nordling lab. Together with me, we have my assistant hackers, Jacob and Rick. But we have a special surprise today because, unfortunately, our usual chat master, Rain, is unavailable today. But in his place, we have Yu Shan. So, would you guys like to say hi to the audience?
Okay. Hello, my name is Rick. I'm a senior hacker of this hackathon, and I'm a master student of the Nordling lab.
Hello, I'm Jacob, and also is the assistant hacker in this hackathon, and also is the master student in Nordling MCKU. Thank you.
Hi, I'm today the Q&A session's host, Yu Shan, and welcome to ask any question in YouTube or in Twitch.
All right, thank you, guys. So Yu Shan is going to be doing a Rain's job today. So, any question that you have, any comment, concern, you can write it down in the chat, and she will let us know, and we will try to answer it to the best that we can. So today we actually have a very interesting topic. Previously, on last week, we worked on object detection to using the OAK-D. Now this week we have something similar but even more special, which is doing post detection, and we will talk a little bit more about that. So let me show you the outline that we have for today. So we will first talk about what is post estimation, and then we will talk about what kind of what different methods are there, for detecting the post of either animals or humans. Typically, it's of humans because we as humans we are interested in looking at humans. And today we will focus on 2D post estimation, and we will talk more specifically about the method that we're going to use today, which is OpenPost. And then at the end we have we'll get our hands dirty and we will do some coding together using this OpenPost model to detect the pose of of in this case it will be me, right? It will be detecting my shoulders, where are my eyes, where is my this part of my body. It's really interesting. You guys will see in a while. But let's start with the introduction of post estimation. So post estimation basically is a task that detects the position of key points and their connections. So for example, here we have this picture of Jacob, which all you guys knows is my assistant hacker right now, and a colleague of ours called Esteban. So basically the point is to get the image right, and in this image we assume that we have this certain object. In this case, this object that we assume that we have is a human body, and the point is to detect key points. So the key points corresponds to joints in our body. Like for example, you can see that let me have my pointer here. So for example, this key point corresponds to the mouth, this key point corresponds to something in the neck, this key points corresponds to the shoulder, elbow, right? And apart from detecting where on the image are these key points, like by having the X and Y locations of the points, we also want to know how do these three points relate to each other, because we need to understand that this point relates to these points, which is a little to below, and not to this other point, right? So that's also an important thing that these algorithms aim to do, to find the relationship of these points. So next we go into the clustering of post estimation methods. So there are actually a lot of post estimation methods. Here I would like if maybe my assistant Jacob could help me to explain to the audience.
Okay.
What?
So as shown in this tree, and the post estimation will be divided into the 2D post and the 3D post. And in 2D post, we have the animal detect, and in the training post and the multi object. And what is different between these two? Because the earlier study can just regress the one person in each frame. So if you want to detect multi-person in one frame, it should be doing the object detection to detect the people first, and then doing the post estimation in those people in box. And so they will be using two models to do this thing, and will be very slow. And so now we will using the multi-object is the new listed method, which can detect the multi-person in one model. So we will be dividing to the top down and the bottom up, and also have the top down adding bottom up. And so for today's OpenPost method, we using the can belong to this bottom up. And for 3D post estimation, will be divided into the monocolor method and binocular method. And what is monocolor is the single camera, and binocular is the multi-camera. And then the single camera, which monocolor can be also be divided into the model 3 and the human model first. And this model is not the machine learning model. This is the actual human model. So so for OpenPost also is not using the real human model. And then it's, I think the lab will be too deep, so I will not explain here because this is not belong to today's topic. So let's see. I think that's all. Thank you.
Yes, thank you, Jacob.
Yeah, I think it's too deep.
Yeah.
Yeah.
So just let me highlight some of the things that you said. So basically, this job is part of a larger work that Jacob has been doing together with Esteban on post estimation. But and they have read many different articles and research about, and they aim to kind of like organize these methods that they see, right? So to my understanding, you basically can at the highest level, we have that post estimation can be divided into 2D post estimation and 3D post estimation. And for 2D post estimation, there is for this thing for detecting animals, and then and multi-object. So multi-object, I assume that here you refer mostly like humans, right, Jacob?
It's correct.
Yeah. So so basically, this multi-object is actually quite interesting because there is top-down training, bottom-up training, which is a very essential key points that we will explain right now. And then for 3D post estimation, we have monocular, which stands for just one camera, and binocular for two cameras. And then monocular basically has this model free, which so there's a human-based model and then a model-free model. And the interesting part of this is that human-based model, basically you put some constraints, right, towards like how the relationship of the key points can be. Because for example, you know that if a key point is here and your elbow is there, there's a certain degree of freedom that your the connection can be in, right? Like for example, let's say what an elbow would very strangely be super above the shoulder, right? So that's the human-based model. There's a model free, and like Jacob said, this is a lot of information, right? Because it's part of a big project. But the main thing here is top down, bottom up, which is you can see that almost all the methods have top down, bottom up at the lowest level, and we will discuss about what is this in a moment. So we will talk about 2D post estimation. So as you saw before, at the highest level, right, post estimation can be divided into 2D post estimation and 3D post estimation. For detecting the pose in multiple objects, in 2D post estimation, there's mainly two ways of doing it: top down and bottom up. And there's also top down and bottom up, right, which is combining the two things together. So here, for example, you could detect the pose of your hand, right? So you can detect like where are these red points are the key points, and then the blue lines are the relationship between all of these points, right? Okay, so for the first method to do 2D pose estimation is top down. So basically for top down, what will happen is that if I have this image, right? I know that there are 1, 2, 3, 4, 5, 6, 7 people. And then what the method will do is it will detect. So you guys are familiar with this detection process from last week. It will detect, it would give me where is a human in this picture. And then I will basically get that picture out and try to detect the pose in the picture, right? For every ROI, for every human that is in the picture, right? So in here, so it will pass through this neural network, and then it will do the pose non-max suppression, and then it will give you the pose for each individual athlete here, or for the ones that it can, right? For example, this one is occluded and this one is occluded, so it cannot tell you the pose from those. I'm not sure that I remember what is a STN, SPPE, STDN. Maybe my assistant hackers can give me a hand on this one.
Yeah, okay. So this model called alpha pose, and this is a top-down method. So for finding the bounding box, for this model, you actually using a single shot detector, which is we discussed last week. So the bounding box here is come from the SSD, and you can imagine like there's a problem for this detecting person. Like you can see the figure, the left figure, no, the left figure, the most left figure, the yellow bounding box. Yeah, you can find this. The person is not actually in the middle of this bounding box. So it's the thing is a problem for a model detect the key point. So for avoiding this problem, he was sent to the STN. STN stands for Spatial Transform Network. This part is doing something coordinate transformation for making the person in the middle of your input image. So after doing this, you will go to the SPVE, which is the single person pose estimator, get the key point. And the second is the SDTN. The SDTN is the inverse of the STN. So it's actually to transfer your coordinate back to your image, your original image. So finally, through the non-maximum version, you can get a final result. That's it.
Thank you, Rick. I think that was an excellent explanation of this flowchart. So then we will talk about. Okay, so this is just the image, just a little bit larger, but the same idea. So yeah. Okay, so the other approach, right, which is the common approach, is to do bottom up, which finds all the key. So you have the image, right, and then from this image you will extract all of the key points, right, and then you will try to classify them. So the way that you do that is you have, for example, this map here. What is this map here? So this map is it's a confidence map of where a key point could be, right? So for example, and in this case, black is so the confidence map tells you in probabilities how likely that there's a key point there. Lighter means that it is more likely to have a key point there. So for example, you can see that OpenPost actually has this defined key point positions, like it tracks the nose, the eyes, the ears, the shoulders, the elbows, right? Like as you can see here, ears, nose, eyes, it will track these points, right? And then those are the points that you can see that these areas that where they have the key point are the areas that light up in the image, right? And similar to and it will do that for all the objects in the image simultaneously. You will find this map that you contain the probable locations of the key points, and then once you have those locations, then it does some pre-processing to actually select the final location, right? The prediction of the location, and then it would analyze. Okay, this join this key point is joined with the other key point through this part affinity field map that is basically a vector field that tells you how are the key points connected. So, for example, you can see here how the it's a little bit a pity that these arrows are a little bit too small on my screen right now, but you can see that basically in Jacobs. So Jacob is this person on the left of the image. You can see how the arrows kind of point that that this node is connected here, right? So the arrow is pointing there, and then the arrows are pointing down, right? Because that's how the part affinity field information is decoded. Like that's how they know that this joint connect to this joint, right? That's how they know this joint connect to this joint, and this joint connect to this joint from the direction of the part affinity field. Yeah, so then once you get these two, you should be able to obtain this nice plot that tells you like where are the key points and the relationship between these key points. Okay, so now we have presented these two approaches. These approaches seem to be very common in the post estimation field. So when would be more suitable to use the top down or the bottom up? Like in which cases should I use the top down or the other method? Well, the top down approach is suitable for in the cases where we have fewer people and require high precision. So for example, video games and remote control. Why is it this case? So the top down, as we saw, it is like this multi-step process where you first detect, right, and then after detection, then you do the post estimation. And as you saw on our previous workshop, just the detection part is a problem in itself, right? And as you saw last time, it's hard to get algorithms that are real time, right? So in the bottom approach is suitable for scenarios that require higher FPS and contain a lot of people, right? Why? Because in this case, the post estimation is done basically at the same time and simultaneously by getting the path, the part affinity fields and the confidence map, and then the thing that will likely take the most computation is the post processing of these things, right? To actually identifying the key points and their relationship. Okay, so we have decided to use OpenPost, as you saw from my table of contents. And why we have decided to do to use OpenPost in this case? Well, because if you see these are just different kind of post estimation methods, and you can see that if we, for example, plot the runtime as a function of the number of people per image, the OpenPost basically doesn't increase, right? So its runtime is low all the time, and it doesn't increase, as opposed to, for example, OpenPost with or for example, mask RCNN interpolated, that you can see that as the number of people increase on the image, it has its performance in terms of computational time decreases because it requires more computation, right, to find these people. And you can see that also OpenPost at max accuracy tends to be a little slower than the normal OpenPost, but the way that it scales is basically is linear, but the slope of this line is basically very small, right? Almost zero. So the line seems like horizontal in this case, or at least until 40 people. So let's talk about a little bit about OpenPost, which is the method that we will use today. So OpenPost is a bottom-up approach for post estimation, and it uses the recursion of stages to improve the predicted pose. That means that for each stage, the output of the confidence and part affinity fields, which from now on you will hear me say a lot, PAF, right? For its acronym, are improved. So what does this actually mean? That it means that at the beginning it will predict a confidence map and a part affinity field, and afterwards, then it will improve, right? So it would take those outputs and pass them again through this same network, and then it would get, for example, at stage 3, it would give you an improvement, right, of both of these things, and then so on and so forth until you get to a stage where you get something that is very good. So for example, in here we want to predict the confidence map. So the ones on the top are the confidence map of a wrist joint, and on the bottom we have the partial affinity fields, or the paths, for the right forearm. And you can see how at the beginning, like, it once you see the image, this is probably because the image is has a lot of people, right? You can see that there's a lot of false positive. There's a lot of areas in the image where there's a high probability that there's a risk, which could lead to a lot of false positives, right? So in this case, they are using this jet color scale. So for the jet color scale, red signifies higher value, so higher probability, and blue signifies lower probability. And you can see that it has this, for example, it has this, it has this right wrist seems not so light up, and then it has also this for example, this part is very light up, this part is also very light up. So, and then for the forearm, you can see that there are some forearms like this one that are not a right forearm. This is a left forearm, right? It's quite interesting to me that it kind of lights up for the opposite part, right? It kind of, you can see that how the network is trying to make the decision. Like, for example, this one is a left wrist, or similar like this, and there are also other false positives here, right? And then as the network goes deeper in stages, then you can see how this one starts to light up more and more and more, and this one starts to decrease, right? Because this is a left wrist, which looks similar to the right wrist, but the model somehow can identify between a left and a right wrist. And also you can see here how at the beginning we used to have these areas which seem to light up a little bit, and then as the stages go deeper and deeper and deeper, then these seem to attenuate, right? And then they leave us with these ones. All right. Okay, so we talked about what is a confidence map and what is a part affinity field. So a confidence map is a 2D representation of the belief about the location of the body parts, and then the model obtaining the body parts by performing non-max oppression. So as I said before, right, a confidence map is basically just a matrix, all right, a tensor of rank 2 that basically contains information of the likelihood that there's a body part there, right? So you can see, so this is just a confidence map of the wrist and how they improve to each of the stages of this OpenPost method. And then in the end, the model needs to perform non-max oppression to identify what is the correct location of the or the most likely location of the key points by looking at clusters of these or areas of the confidence map where they are lit up, right? Okay. Now, in addition to the prediction of the key points, we will need to find association among the key points, right? So for example, let's say that I have this in this image, I find these 3 key points, or these 6 key points. So 3 for the top of the neck, and 3, let's say, for the middle of the hip. So in theory, all of these nodes could be interconnected, right? But in practice, we know that no, one person only has one node on the top of their head, of their neck, and one node at the bottom of their hip, right? So we know that, for example, from looking at this, that from all the possible combinations of nodes, that these green ones are actually not they are not suitable, right? For our case, because that will mean that this node is connected to the neck node of one person is connected to the hip node of another person, and that's not what we want, right? We want the node of a person the neck node of a person to be connected to their same hip node, and that's what we see here. And then here, and we use the part affinity fields to define or to establish that relationship between these nodes, right? Okay, so the part affinity field is just a part-to-part association of the key points, and each part affinity field is a 2D vector field of each limb. So basically, that's so what is the shape of a part affinity field, right? So it's just like it's like a matrix, right? A rank 2 tensor, but well, a rank 3 tensor now. But at each pixel, you will have information of the x and the y coordinates of where the connection could be, right? So you can see, for example, and this connection should be between along the line of the key point. It should be stronger than any other direction. Okay, so this is the OpenPost model. In here, I would like maybe Rick or Jacob to explain to the audience how does this model actually work.
Okay. So this is like a pipeline of the OpenPost. So you can see the top of this is a stage T. Is mean they will have many stages. So the first input, the F, is actually the feature from original input image. So they will pass their input image to a VGG19, their convolution layer, to get this feature map, and the feature map will go into their structure to predict the path and the confidence map. So the green part is the blue part is for predict the path, and the result of the path will send to the next block, which is orange, for predict the confidence map, and also the feature map will also send to the block for predict the confidence map. And after this, after repeat several times, several stage, you will get a final result. And here after this convolution block and the one-time-one convolution layer, we will get several image represent how many paths we have. For example, if we have, this depends on your model. If, for example, you have 19 joints, you will get 19 future map output. So there's a brief explain of this pipeline. Thank you.
All right, thank you, Rick. So I assume that this is for just one stage, right? Yeah, this is stage T, so this is just for one stage, and then the next stage will be you will send the information back, and then it will be better iteratively. Okay, so now we have the map of this connection of each key point for the Figma model, but this is, I would like to clarify, this is for OpenPost, right? So we can see that, for example, in OpenPost, this is a node 0, and this so each node will have their own index, right? And then you can see how, and this will be useful for us later when we do some visualization experiment. And yeah, so I will actually have this figure up later for you guys to see. Okay, so we're going to start our coding session for today using the OpenPost model. You can, as always, you should be able to find our code in this link. Maybe Yu Shan or our streamer can help me post this link on the chat so that people are able to access it. And in here, you should also be able to find our slides for this. Okay, so before we start with the code, we're gonna take a 5 minutes break, okay? And then we will come back very soon. Okay, welcome everybody. I hope that you guys had a nice break. So first, I would like to just demonstrate how can you access the code. So you just grab this link here. Oh, let me make my pointer. You just copy this link here, and it will take you out to this repository called Nordling Lab OpenCV and AI Hackathon. And here you will be able to see the code not only for this week, but from all the other weeks. And it will also give you a link to our workshops. It will tell you about what did we do, right? It will also give you the code for the 3D CNN that we trained on week 3. Here I would like to also reference the slides. Maybe we're thinking about adding, well, the slides I think should be able to find it in here as well. Then you can just clone this repository using Git Bash or any other Git system that you have, and then it will basically, what you will get is something like this. Not this one. It will be like this thing, and then you will have week 5, and then it will contain a lot of code inside, and also the model that you need to run this code. So typically, excuse me for 1 second while I organize my windows. Okay, so typically what we do is that we start by showing diagrams of the code, right? And then we dig into the code, and then to the point that we get the result, right? In this case, I would like to switch the things and make a little bit different. So I'm going to start by showing you the result. Oh, but I'm just running the post. You can run post estimation.py. All right. So this is a code that we have prepared for you guys. And you can see how it is detecting, depending on how I stand, my ears, my eyes, my nose, this point in my chest, my shoulders, right, and my elbows, and it's drawing lines. It's drawing lines to find the relationship. So if maybe I can stand to show you guys how does it. So when I stand, it is able to detect more points. Okay. All right. Okay, I think you guys have seen how it works. And the slides that we have, the images that I have on the slides are basically the results of these things. So now we're gonna dig into how do we actually get there, right? Because I think this code is a little bit more complex than the other codes. well, in terms of the post processing. So here we have the host device diagram, and we introduce this new node, which is called the neural network node. And here I would like to have maybe Rick explain this diagram.
Okay. So inside one device size, very simple. We just need a color camera to get our input image, then send to the neural network, the node called neural network, and the neural network node will send out the result, the predict result of confidence map and path. But for this model, the big point is the post processing because we got the path and confidence map and we need to code it. It's not very simple, very directly just plot it. You need to do something, and you will see later. So that's my explanation.
All right. Yeah. So one of the things that I would like to just comment on is that on week 4, so week 4 we did the face detection. So you saw that we had this. So week 4 we did the face detection. So you saw that we had this SSD model, right? And the node that we created was a SSD detector. So there, Depth AI has this defined nodes, right? Where they know that you want to do object detection and which architecture you want to use. So they have that node for you, and what you can extract from that is simply the detections, right? So you can extract the bounding box information. For the post estimation, it's not as simple to do that. That's because there's not like this unified like skeleton, right? And also there are many methods to use. So I believe that's the reason for why there's not this, for example, this OpenPost post detection node. So we'll need to do some something a little bit more than just getting the detections. And now we will go to so we treat this network as a typical neural network, and that's why we need to just define at which layer do we need to extract the information and stuff like that. So now we go into the flow chart of the algorithm. So maybe here for this one, maybe Jacob can explain.
Okay, so as shown in this slide is the flow chart that's OpenPost running on the Oakley device. So just like we said in the host device diagram, first the key point confidence map and path affinity field map will be predict. And then since the key point be predict with the order, we can get a possible connection based on the key points confidence map. However, there will be a lot of the possible pair, but there just has a one correct connection. So therefore, setting the 10 interpolate point in each pair, and we will finding the path value as each interpolate location based on the projection. So those path value will be doing some the inter productor process and getting a score, and this score will be compared with some threshold, and if passed, there will be saved as a valid pair. But here you guys can see in the valid pair one the figure. So we're using the apps as an example. My app has the connection with the Ric's app. So, but it's actually this connection is not correct and incorrect. So, however, don't forget we have this called path affinities field, which you can also call the path. So we can based on the path, we can get in the correlation connection of the valid pair. So showing in the final one is the the result. Thank you.
I'm sorry. So now I'm gonna show you the code for this part. So basically, if you go into the directory and you look for the post estimation part, here we have this code which I will go through. So here we have just separated this code and made comments on what is each chunk of things doing. So in here, I just like to mention that uh, all of this code is necessary for us to be able to detect the key points. But for example, in this part, it's like because you need to analyze different key points for different persons, and you need to analyze each key point with other key points, right? So it goes into this nested loop, which is I believe like 4 levels down or 5 levels down. So 1, 2, 3, 4, 5 levels down. So that means that it will be very hard for me to do this to code all of this in front of you for this hackathon part, and it's 150 lines of code. In practice, the code is not necessarily long, but it does contain a lot of math, and it also contains a lot of nested loops, which kind of makes it like very kind of hard to imagine how this code is working. I also think for pedagogical purposes, we will focus mainly on analyzing the paths. So visualizing the part of the confidence map first. We'll visualize the confidence map first, right? And what can you do to kind of like filter out unnecessary things from the confidence map. And in addition, we will also visualize the path. So so how do you actually get to that map where you saw before that they had the arrows, right, that show the connection between each key point. Okay, so the first thing that we always do, for those of you who have been here since the first workshop, is we need to import the required packages, right? So in here, we actually, if you also look into your into your uh, into your directory, you will see that you have this post info directory inside the repository. So in here, we basically wrote 2 Python scripts that tell you like just specific information about the neural network. So here you have, so the first one is the code, and then which is also here, and then the next one is plotting. So why we created these packages is because this contains specific information about the neural network, like for example, what is the model name. It contains what specific frame size does the model require in order for it to do the predictions. It contains the layer that you need to name in order for you to extract, and so on and so forth. I don't want to get too deep into these values because they're just like specific values, right, that you need for the code to run. But in here, you basically import them by using from this directory, and then the script name. You can import. Well, here we imported all of them one by one. Another option that you could do is just import all of them using this star, right? So that will import all of them. But then I also think it's for pedagogical purposes, it's better to import each one, because it tells you, okay, it kind of tells you that which variables do you have, right? I suppose that if I import it with the star, I wouldn't know what is inside. So you can do the same thing with the post info decode. So in the decode, we have the model path, the frame size, the key point confidence layer, key point confidence shape, the path layer, path shape, All right. And then we define our pipeline. So this pipeline, as you can see, is actually shorter. It's shorter and much more simpler than our previous pipelines. And that is reflected also on our host device interaction diagram. So basically here, this pipeline is just is the function that requires the blob path, right? So blob is just the model. It requires a preview size, right? Because each model requires a specific preview size for it to work. And then you define your pipeline by saying die pipeline. You have your cam RGB, which is gray color camera. You set the preview size to the specific preview size that you, in this case, the preview size is just frame size, which is a parameter that we imported from our, you know, from our uh, from a specific values, right? Then we have this cam RGB. You send it to interleave because we want to have a, otherwise you if we want to have a planar uh, data structure, right? Not interleave. That's for it for a network to do the predictions correctly. And then we have the X out node. And then we have and for creating the new network is as simple as that. So just create a new network node, and then you set the blob path to whatever path you have for your model, which in this case is just this one, right? Then you create the Xlink out node, and then you set the stream name. And then the last thing is to link the stuff together. So let me pull out the the diagrams. So that we can see. All right. So from this diagram, you see that we just have the color camera, and that's the camera that we have here. That we have the X-Link out here, and that is here. And then we have this neural network node, which is the OpenPost model. And then finally, we only have the X-Link out, and this also here. And for the linking, you just link the camera with the OpenPost model, which is here. We have the camera with its respective X-Link out node here. And then finally, we just require the output of the post estimation model to go to the X-Link out. And then as we have done with on the other weeks, we get the pipeline. Get the pipeline. We start create a device to which we assign our pipeline. We start a device, and then we can start getting our queues, right? So our queues is first this QRGB, which is we gonna take stuff from the queue named RGB, which is our the preview for camera with max size 1 blocking equals false. Our queue of post detections is just this, and then we just extracting the stuff from the post neural network. Okay. And then we go, so then we initialize some values that we need, and then we have our post processing. So what are we gonna do once we get those items from the queue? So the first thing is to get the RGB, and then, as you remember from last time when we're dealing with neural networks, it's better for us to do try get, because not all the time are we gonna get a detection, right? So it's easier for us to avoid bugs. We have this try get, and then we converted our in RGB into a CV frame. Okay. So regarding our detection, so if we have detections, then we're going to extract the confidence map, and the confidence map is like this. It's just the detections. From the detections, we're gonna get at get layer F16. This F16 is just floating point 16. From which layer? right? Is key point confidence layer. I believe this is from the code. So this is just the name of that layer at which the confidence maps are in, and we're going to reshape them because you're gonna get this as a single vector, right? And then we are going, and we will demonstrate all of this a little bit later. But you need to reshape them into this shape, right? You want it as a 1, 19, 32, and 57. That is because you have 19. Uh, you have 19 key points, and then you also have and and basically you have each map being 32 times 57, and the same thing we have for the paths. Okay, so then once we get these two things, right, then the first thing is we're going to analyze our confidence map. So our confidence map is just um, here. So we're just gonna extract the first one, for example. We're gonna go through them one by one. We're going to resize them because they are 32 times 57. We want to compare how do they look with respective to our original image. So we want to make them the size of our original image. So that's why we resize them to the frame size. Then as so the confidence map can contain areas where they're light up as you saw in the presentation, but they're not necessarily where a key point could be, right? So we filter out by just filtering out where in this confidence map has a value above than a threshold. So we basically binarize the image, right? And then we find contours on that image. Then for each contour, we basically do this function, which is field convex poly. So field convex poly is just, you have the contour and then you basically just color in inside that contour. That's gonna give you a blob map. And then with the blob map, you can multiply that with the probability map to then basically obtain the areas that are above that value, right? And then you're gonna then from that area, then you are going to get the maximum location and what is the max value. So let's pretend that I have an image, right? And it has so I have different blobs in the image. So the contour parts will give me the part. So it will give me this a blob in one location, and then it will give me the different blob in a different location, right? So it will kind of separate the blobs for me. Then for each blob, I need to look where is the maximum value of that blob, and what is that maximum value, and then I'm gonna append that into my key point list. Okay, so then I'm just gonna append this one is just appending ID to the key points so that we can identify them later. And then now is for, so now we're gonna analyze the path. So the path is just so in here we identify that the a path X is this is at this index, right? And then path Y is at this index. So this contain information of where are the arrows, uh, how are the connections of the key points, right? Which are represented by arrows. So here we're just going to resize this to the same size of our frame size. And then we're going to define candidate key points. So you're gonna have this new key points is a variable that we have created before. And then we're gonna go through each candidate key points pair to identify if they're a valid pair, right? And the way that we identify if it's a valid pair is the following. So the first is that you normalize the vector, the residual vector of the candidate key points. Okay, let me delete this. So this is basically just following the OpenPost paper. You normalize the residual vector of the candidate key point pairs to unit length. So you have the norm of the residual vector from candidate key point A and candidate key point B. Well, candidate key point B and A is yeah. Then you basically normalize it using by dividing by this norm. So that means that you're gonna get values between -1 and 1, right? For this vector. Then we will interpolate the location of the candidate key points. So that means that so here just interpolating the locations with number of interpolate samples. So we're gonna interpolate on the x. So here we have a linspace, so it's create linearly spaced points, right? And you basically are telling it to interpolate for n interpolate samples. I believe this should be 10. Yes, this should be 10 defined here. So let's say that, for example, I have a what? Let's say this number is 15, and then this number is what? 35. So then it will create 15, 17, 19, and give you 10 points from that interpolation. And then we need to find the path value at each interpolated location, right? And okay, so then once we have that, we can define a path projection score and an average similarity between the interpolated path and the residual length, the normalized residual unit vector. And then if they fulfill this criteria, then we append them as a valid pair. So they need to be the path projection score need to be greater than this value. I think this threshold they define as 0.4, and they define this max score as first as -1, but then they will be updating it, right? You'll be updating as we go through more candidate key points. Then we find the connection, when the correct connection in the valid pairs. We save the connections if it is in the valid pairs. And then this part is just to plot. So here this nested for loop is just to plot in the RGB frame the detected key points, right? And then this part here is just to draw the arrows that you saw from each key point to the other. Okay, so as I mentioned before, in a few minutes, I'm going to just go through this first part. So I'm going to import, create my pipeline and everything, and then we're going to visualize the confidence map and the part affinity fields after a 5 minutes break. So can maybe my streamer take me to a 5 minutes break now? Okay, welcome everybody to now the most fun part of this hackathon session, which is the coding. So the first thing will be, let's get to it. Well, let's get to it without any delay. So can you see my code? Is that okay? Okay, good. So the first thing is to import all the required packages. We have done this so many times. So import CV2, import CV2, import dep AI as die, import numpy as np. Then the next thing will be to import the stuff from the subfolders that we have given you, right? So in this case, we have from post info.decode import, and you can import all of them like this, but in this case I would like to just write them all, because then it kind of helps me remember what variables do I have. So in this case I have model path, which is the name of my model. Import what else? Frame size, import key point confidence layer. Oh, not import again. key point, confidence, shape, path, layer, path, shape. Okay, so I think that's the only thing that I'm gonna read for right now. And then from post info dot plotting, we're going to import what? What else are we going to import? So the first thing is post pairs. Import map uh, map idx. Import colors. Import well, I'm not sure if I'm gonna need this, but I'm gonna import them still. Pairs num and key points num. All right. So as always, it is essential to run the code. So I'm gonna run test.py right now at every stage of your development to check if it is working. It is indeed working. Okay. So let me put that to the side. Then the next thing will be to define a pipeline. So you're gonna define a function that's gonna be called create post estimation pipeline. Okay, that's gonna be pipeline equals to depth.ai dot pipeline big P. Going to return my pipeline equals create post estimation pipeline. Okay, so let me save and run. Okay, it didn't give me an error, so that means it's probably working. So the next step will be to so the color camera node, right? So cam RGB is going to be pipeline dot create color camera node. Then cam RGB is going to set preview size. Now, in this case, we already have the size that we need for the neural network. So I'm just gonna copy this frame size here to build my preview size. I'm going to see cam RGB set interleaved false, because this is what you need to do in order for the neural network to predict the images directly. What else are we gonna do? Let's create the output node. So X outcome RGB is pipeline create X link out and X out cam RGB set stream name. Let's set it as RGB, and then we're gonna just print something so that we can know that we actually run this part of the code correctly. So created color camera node. So let me run this part again. Okay, so it gave me this message. So that means that it's actually doing until this part. What else? So the next thing will be to create this post neural network, which is going to be pipeline create neural network node. Post neural network is going to set when the model needs to know, okay, which network do you want to set up here, right? So we need to say set develop path. We're going to set it to model path, right? Because I also need to make this an argument in my function. All right. And then lastly, we can just create the X out post neural network. That's gonna be pipeline create new neural network. Oh, sorry, no, not pipeline. It will be create. Sorry, X-link out. X-link out node, and then finally we need to set the stream name. Stream name to our output of the neural network, which is just gonna be post neural network, right? And we're gonna print something so that I can know that it's actually doing these things. Create the post neural network node. Save it and run it. All right, so it's creating the color camera, the neural network node. Since this is a very simple a pipeline, then we just that's the only all the nodes that we need, and then we go to link. So linking. So what links with what? Well, the preview of the CAM RGB is going to be linked with two things. The first thing is gonna be linked to the post neural networks input. And the next one is gonna be CAM RGB. Its preview is going to be linked to the X-link out node, the X out CAM RGB input. And finally, we have the output of our post neural network out is going to be linked to its respective X-link out node. Okay, and like I've done always, I'm gonna print finished creating pipeline. Okay, so it's doing all of them. Okay, so now we just start our device. We say device equals depth.ai device, and we need to assign this device a pipeline. So this in this case is just a pipeline that we have created. Oh my god, no. All right, and then we just start a pipeline device as easy as the start pipeline. So now I'm gonna save and run. I just like to mention that at this point you should be able to notice that if you have your OGD connected, that it makes this little sound like if you had connected a USB, which in my case it did it. So now we're gonna define our queues. So QRGB is gonna be device get output queue. All right. So which queue? We need to define that. So QRGB is gonna get the stuff from RGB. Gonna have a max size of 1 and a blocking behavior of false. Then Q, let's name it post detections. Is going to be device dot get output Q. From which Q? Well, from the post. I think we name it post neural network. Gonna have also a max size of 1 and a blocking behavior of false. All right, save that. And now we can get into the actual uh, manipulation of what these items in the queues. So while true, so the first thing we need to do is get items from our queues. So we go that in RGB is Q RGB get and Q, sorry, in post detections is so in this case we're not necessarily going to have detections all the time, right? So for us it's better to do it instead of getting get, you need to use try get. So Q post detections try get. All right, then we need to convert our in RGB as to a CV frame. So RGB frame is going to be in RGB get CV frame, and now with this one we can start print. We can do CV2 I am show. We can show it. CV2 I am show RGB frame and show what RGB frame, and we need to define a condition to terminate our for loop CV2 if CV2 wait key 1 is equal to the ordinator key Q, then we're going to break the for loop. So okay, so right now it's just getting the detections, and it's just gonna plot this this RGB image. So let me run it. Let me see if it runs or am I gonna get an error. All right, okay, so it is working. Nice. So here I would just like to make note that this frame is 456. If I'm not mistaken, 456 times 256. That's because that's the size that the OpenPost model requires for it in order to do the prediction. All right. Okay, so we have this. Now, what is the next step? We need to check if we have a detection or not, because there could be cases where nobody's on the image and there's no detections, right? So we need to check. So if in post detections is not none, then what? Then we can extract stuff from each layer of the neural network. So we call it conf map. Another case something is called conf map is going to be no, in detections, in post detections, get layer floating point 16. Okay, at which layer? Well, that layer is going to be the key point confidence layer, which is the, if you would like to see it, is just MCOM stage L2. So this is just some naming system that they have, but I think this is much more easy. It's just easier for me to understand. I'm gonna tell it to give me this thing. Now, let me show you. Let me show you what I get if I just print the shape of this thing. And I tell it print me. Okay, could you print me the shape of this confidence map? And let me run this. Okay, so you can see this is it's telling me that the shape of this thing is 34,656, but I know that this is just a series of maps, right? Because as you saw before, this for each key point, we're going to have a map that tells us where in the image could we have a nose, or where in the image could we have an ear or a shoulder, or so on and so forth. So I need to reshape this. Reshape it to what shape? So the shape is key point confidence shape, which is 1 times 19 times 32 times 57, right? We have 19 maps that are 32 times 57. All right. So we just reshape it to the key point confidence shape. All right. And now, well, now the shape obviously is going to be 1 times 19 times 32 times 57, because I reshape it like that, right? So the next thing I'm gonna do is to get my paths. It's going to be the same thing, a numpy array, which is in post detections get layer as a floating point 16. Which layer? And that's why we also have a path layer. All right, that path layer is like another mconv, something like that. Mconv stage 2 L1. Yeah, so it's just easier for me to call it path layer. And I need to reshape that, right? Reshape it as what? Well, as my path shape, which is 1 times 38 times 32 times 57. One thing that I would like you to notice is that, well, if you haven't noticed it, is that this 32 times 57 is the same for the path and for the key point confidence shape. That's because these two aim to represent the spatial, spatial locations of, the original image, right? Okay, so now it's getting crazy. Okay. Now we need to iterate towards through every. So now let me start by visualizing the confidence maps. Okay. So the first thing that I need to do is okay. So for I in range, okay. Um. Right in range of, I think it should be something like that is 19. So probably pairs num, if I'm not mistaken. Then I'm gonna do what? Then I'm going to get my probability map, which is a confidence map for a single key point. Okay, so let me so what I want to do right now is that I have probability maps of where my key point could be, right? But right now, what I want to do is just I want to binarize my image just based on a threshold, and then I want to use that mask to then remove all the unnecessary or all the values that are less than that specific threshold, right? So what that's gonna be my masked probability map. It's gonna be an empty list where I'm going to just store everything here. So let me just start by saying that, for example, my prop map would just be the confidence map, because it has a 1 at the beginning, so it's always the 0th element, then it's I, then it's the whole two-dimensional thing, 32 times 57. Okay. What happens if I then just for fun I do mask? Well, let me make it a list. Mask prop map list. I append prop map. Prop map Okay, and then I show it. So I CV2 I am show mask prop up, and then I have my mask prop map list, and I'm gonna show just the first one. Okay, so let's see what happens if I do this. Oh, too small. Okay. I see. The first thing I need to do is to resize this. I need to resize this because right now this is at 32 times 57, right? So now it's giving me a window that is super small. So I need to resize this. So CV2 resize. Gonna be my prop map. Which size? Well, it's gonna be my frame size. All right. Okay, now I will run it. Okay. So here I also have the first element of my key point. This is the probability map of where in the image is key point 0. So key point 0 is, in this case, is here you can see that basically if I move my head, the key point moves with me, right? Okay, let me try with a different key point. Let me try with key point what? 3 or 6. Okay, and you can see key point 3, if I'm not mistaken, is the elbow, right? So it's showing like, you can see how, if I overlay the two images, how this bright white part would come to just above my elbow, and you can see that it's actually quite impressive that it can distinguish between my left and my right elbow. All right, and you can do that for any part that you would like. Hacker, my little hackers, what do you like to? What part do you want me to choose? Pick a number.
Actually, I feel a little strange as the line 50 45 because it should be because it depends on our key point number, so this should be the key point number,
All
which
right,
is
key point number.
yeah.
Key points no. All right. Okay. But yeah, pick a number between 1 and 18 or whatever. Which one would you like to choose? Okay, let's do 6. Let's do the other one. It's just to try the different. It's just to demo this side. All right. So now you can see that it's actually then it's the other elbow that is being shown as a very strong color. Okay, good. So now, well, so let's mask this so that we can remove values that are below this threshold. So then after this, what we can do is that we can threshold uh, you can have a map mask, which is uint, I'm going to say uint 8 of wherever wherever in my probability map is larger than, I think the value that they use is 0.2, if I'm not mistaken. And then simply, so my map prob mask, so what is that? Print print the value of my map the empty max. Oh, is it an MP? Let me run this one. Okay. So this basically tells you like one where it has a values above that and zeros for everything that is below. So I can multiply this mask by my prob mask to get a map pros mask. So my mask prob map is simply my prob map, my prob map times my mask, my mask map mask. All right, and then I'm gonna append my mask prob mask. All right. So now what I'm supposed to be getting here are just maps, confidence maps that are a little bit cleaner. You see how now you saw before my elbow was not really that good, and now there's this clear part where there could be my elbow. So let me try with the zero, but the zero was actually pretty good as well from the beginning. But you can see that there's a much more clearer area of where, well, not here, this is my nose, of where the key point could be, right? As opposed if we didn't have this. All right. So now that's for that. Then now I'm gonna go and look and visualize my map, my paths. So for I in range and for the paths, actually we need to go to the length of map IDX, and then we have two paths. One path is going to tell me about the x direction. One path is going to give me the y direction. So let's call it path x is going to be paths, the zero element. And in this case, it is a map IDX I, the zero element. In this case, I think it should be post pairs, no? In this case, it should be post or number of posts. It should be pairs num minus pairs num, and then all of them. And then my path y is going to be my paths, the first element, because we start with OS1, then map IDX, the ith element, and then the second one, minus pairs num, and then all of them. All right. Okay, then the next step is to resize them, because remember that these are size 32 times 57. So path x is going to be TV to resize of path X to what shape to the frame size, and then path Y is going to be CV to resize of, well, path Y, same thing as frame size. All right, and I'm gonna create a variable. So let me create a list outside. So let me call it path display list. So for my path display variable, I want to create a map that is full of zeros. So it's gonna be a black map, as you saw in the image before in the presentation. And then in that black map, I'm gonna just pick some equidistant point, and then I'm just gonna for that point, I'm gonna draw arrows, right? And the arrows are determined by the path, and that's gonna tell me like how is it key point connected with another key point. We will see a little bit more about that right now. Let me start by defining my path disp as just a numpy zeros array. So that means that it's going to be something black, right? A black screen. Now it's actually a little bit funny because in OpenCV the X and Y are like reversed as opposed to numpy. So in this case we need to set frame size 1 and then frame size 0, and we need to set it as a tuple. Okay, but now we have this black thing. Now we need to draw arrows, equidistant arrows, right? So we need to iterate for j in range, and let me start from 1 to 9, and then for k in range, also from 1 to 9. And okay, so the next thing is like, okay, where are my points going to be? So I have my x1 is simply going to be my frame size 0 divided by 10, and then I'm going to multiply this times times j. Yeah, and then I'm gonna make that an int because I need these points to be integers so that I can plot them. All right, so that's gonna be my first point. My y is my point is gonna be defined by x1 y1. So same thing with this y1. So frame size, in this case 1 divided by 10, and I'm gonna multiply. So let's say that I iterate in my y coordinates through k. And then I need to make this an int. All right, so my next point is just going to be a point. So let's say the back part of my arrow is an x1 y1, then my arrow is going to point into what x2 y2. So x2 is just x1 plus path x at x1 x1 y1 times some scale. So this scale is useful because the path, they contain values that are very close to 0. They are 0 mean, and the distribution of those values, the standard deviation of those values is very small. So they are like decimal points, but usually between 0 and 1, or -1 and 1. So I need to define a scale that's going to help me make this arrow bigger, because otherwise the arrows will be just very small. Let me set that to 50 or something like that. And I need to make that as an integer as well. All right, and then my y2 is similar to this one. This is just going to be y1 plus, in this case, is path y at x1 y1 times scale. And then we need to draw CV2. We need to draw arrows. So I think the function is arrow line. Okay. And where do we want to plot this? We want to plot this in path this thing so then the first point is, where does it start? So it's x1 y1, and then the next point would be x2 y2. Then I think the next one is a color. So let me make it 255 to make it white. And then the line width. Is there anything else that I'm missing?
The line style.
Oh, so what is it? CV2 what?
The line AA.
Oh, line AA. Yes. All right. And then I'm gonna append that. I'm gonna append that to my path disk list. And then I'm going to my path disk list. I'm going to add not here. That will be very wrong. It's gonna be here. It's going to append the path disk thing. All right. So with this, I can also plot then my path disk. And this is going to contain path disk. No, not this. List, and then whatever element I want. So in this case, let me start with 0. Okay, so let me run this to see what do I get. Okay. Oh, that's true because I have only y1. All right, that's just a small bug. Okay. What is it? Is it index 273 out of, is it reverse x1 y1?
I think should be y first.
Y first. Yeah, I think this is tricky. Okay. What about here? Here should be x first, y first, right? Sorry, x and then y. I think so, right?
Yeah, that's right.
Aha. Okay, so now I'm getting these 3 maps. And what does this map tell me? Well, so the first element of my path disk, let me show you here, is this tells me about the post pairs 1 and 2. Okay, so let me actually draw this thing a little bit more clear. So let me have this prop map list of 1, and then 2, right? Let me run this. Oh, what? I didn't save it. Control save and then run it. All right. So now I have this and this. So if we get out the image, so it's telling me that node 1 is at the middle of my chest, right? which is, yeah, it seems like this is correct, like this could be node 1, and node 2 is at my elbow, well, at this elbow, right? And then the path this is telling me that, yo, it's telling me like from this node to go to node 2, from node 1 to node 2, this is the vector field that you need to follow, right? You can see that the arrows are actually quite strong right now. What about then for number 2, right? Like let's check out the second element of my path disk. That is supposed to be from what? From 1 to 5. So in 1 to 5, if we look at the image, is to the other shoulder, right? So let's see. And then let me, instead of 2, I'm gonna have 5. And let's run that. All right, let's run this. So now I'm picking the number 1 is still here, number 5 is here, and now it's telling me, hey, to go from number 1 to number 5, you need to go that direction, right? Follow this direction of the arrow. And then let's do one more. So let's pick 2, 3 or something like that, just to finish our demonstration for today. Let's pick out 2, 3. So it will be just the third one. That's from my shoulder to my elbow. All right, and you can see how the arrows are just pointing. Well, they're pointing down like this, right? Very strongly from my shoulder to my elbow. And that now with this information, you should be able to do a little bit more post processing to then find the valid pairs, and identify which that these nodes are from one person, these nodes are from a different person, right? And then with that, you should be able to plot the same plot as we have before with the different colors. Now we have reached we're almost reaching our time limit for today of 2 hours. So I would just like to thank all of you who have been watching us. I would like to thank Dr. Nordling for being the lead chair of this workshop. I would like to thank all my different lab members who make this work possible, from the person who made the posters, from the person who was arranging the meetings with the speakers, to the streamer, to the hackers who have been studying very hard and learning a lot with the OGDIV with me, to the chair master. And if I'm forgetting somebody, please forgive me, because there's like so many people behind us. I'm the one who is in front of the camera most of the time, but behind me there's a lot of people supporting me, and this would not be possible without all of them. And also you who is watching us, thank you for your support. Thank you to all our sponsors and to NCKU for allowing us to do this workshop. And with that, I would just like to finish our final official hackathon, and I will just hope to keep doing more of this in the future. Thank you.